So let me say a couple words about next homework. So we'll start off. Let G be a group and X, Y, any two elements of G. We say the commutator. So this is a particular way that you can make a new element of the group from the old. Sometimes written this way is the commutator of X and Y. It's X inverse Y inverse X and Y. And we define the commutator subgroup to be the group generated by all commutators. So you just take all commutators and see the smallest group they generated. Number 1A, show that the elements X and Y and G commute if and only if the commutator is 1. So that's actually fairly easy to see that that's 1 that the elements commute and vice versa. Show that the set of commutators, not the commutator group, just the set itself, is closed under inverses and conjugation. That is, if XY is a commutator and G is an element of G, show that XY inverse and G inverse XYG are both still commutators. Show that G prime is a normal subgroup of G, and I'm going to tell you what a normal subgroup is here in a minute. And show that if N is a normal subgroup of G, then G mod N is abelian if and only if N contains the commutator subgroup. Number 2, let G be a group and H a subgroup of G. Show that if the index of G and H is 2, and what that essentially means is that H is half the elements of G. It's a subgroup that comprises half of it. We'll talk more about this today. Show that H is a normal subgroup of G. Is the same true if the index of H and G is 3, so if H is only a third of it. Number 3, in this problem, we produce some examples and illustrate some things that can happen in normal subgroups. 3A is very computational. Just take the quaternion group we talked about earlier in class and just show every subgroup is normal. Show that N is a normal subgroup of G and H is a subgroup of G. The intersection of N and H is normal in H. And finally, is the notion of normal subgroup transitive. That is, if K is a normal subgroup of H and H is a normal subgroup of G, does this mean that K is normal in G? Prove this or get the counterexample. And finally, the other problem, if you like, for extra credit, let G be a group with center ZG. Show that G is abelian if and only if G mod the center of G is sigma. Now, there's some of this notation here. You don't know what it is yet. We'll get to this very soon. Okay, any questions thus far? All righty. Okay, so I did use the word normal a lot. I talked about this problem set. So I guess the best to tell you what a normal subgroup is. Quotient groups and homomorphisms. So I'm going to introduce something that looks very much like this thing we talked about, the normalizer. Let me start with an example. Okay, I want to look at the symmetry S3. Okay, this is an old friend part. And I will look at a couple of subgroups of this. One of these groups is better than the other. One of these subgroups is in a certain sense. Right? So Okay. Pick an element for me. An element G. Okay, it's a good choice. Let me point out that X inverse is also 1, 3. Everybody agree with that? Okay, so I want to look now at X inverse in X. This will be practice. This is. So I've got that here. Now, let's do this computation. This is just 1, 3 times itself, so this is the idea. Do I agree with that? Okay. See, where does 1 go? It goes to 3, 1, 3. Okay, where does 3 go? It goes to 1, 2, it's done. 2 better go 1, but I'll check this. 2 goes to 3 and back. Right here. Now let's do the last one. This one right here. Okay, where does 1 go? It goes to 3 to 2. It's done. 2 goes to 1 and then to 3. And 3 goes to 1 to 3 to 1. Everybody up here? You get n back, admittedly in a different order, but you get the set back. It's the same collection of elements. If you had picked 1, 2, 3 and 1, 3, 2, you would have gotten n back as well, because 1, 3, 2 and 1, 2, 3 are already in n, right? So you'll get those back. And actually, it doesn't matter. You picked 1, 3, but if you had picked 1, 2, 2, 3, it would still work. In fact, you can do the computation if you like for all X and G. When you go through and do this computation, you get n back. In general, this doesn't happen. Otherwise, I'm kind of wasting your time. Sophia, give me an element of S3 again. 2, 3. Now, here H is this thing. So this is going to be 2, 3, E, 2, 3. And 2, 3, 1, 1, 2, 2. Have I agreed? Just E again. Agree? What about this other bit? Well, let's see. 1 goes to 2, which goes to 3. 3 goes to 2, 1. And 2 goes to 3 and back to 2. 2 goes to itself. This is not. In fact, it rarely is. If we'll practice. We conjugate H by this other element, 1, 2, 3. This gives me one goes to two, one, three. Three goes to one, two, one, and two better go to so and it goes. Notice with the first example we did with the n that had the three elements in it, when we conjugated that by any element, it might have turned the orders of the elements around a little bit, but you got the same set. Here, you sometimes get a different one, right? So this inspires the following definition, and it turns out that this concept of whether or not this happens is very important. Definition. Let's suppose that G is a group and N is a subgroup. And N and G subgroup. We say N is normal G. Or a normal subgroup G. And I'll use this kind of, instead of the left center equal, you close the triangle off. N is normal in G. If G inverse and this has to hold for all G in N. Equivalently, and so I'll leave it as an exercise for you. Equivalently, this is an easy way to tell. G inverse in G is an element of N. For all G and G, G and G, N.
And that's why you used to prove one of the questions on the homework for homework 3.
Yes.
Should be for all the.
That was the one thing that's more.
Oh. Yes, for all G and G. Thank you. That's very important. By the way, let me point out, this is always true for all G and N, right? Because N is contained, if G is an N, then this is certainly not contained in N. No, that's right. This is absolutely important here. Typo here. Equivalently, G inverse in G is contained in N for all G and G and N and N. And equivalently from that, the normalizer in G of N, using our earlier notation, is all of G. So, let me point out, if G E G is normal in itself, right, in a very silly way. And there's also another subgroup that's always normal.
In the elements.
Yeah. That subgroup is also. In S3, for an exhaustive list, so you should check this and make sure if you want to kind of get your feet wet and figuring out what things are normal. And S3, the normal subgroups of it. S3, the identity, and that subgroup. how many elements are there in S3?
6.
6. There's 3 in here. That's half the elements. That's one of the homework problems from next week. Show that if you have a subgroup of index 2, that is, it takes up half the group, it's always has to be normal. There are 3 subgroups, this, that are not normal. Uh, here's one for you. Yeah. G was blank. There's more than one answer. So then all subgroups of G are normal. Are you able?
I know, it's a dealing in.
Okay, that is correct.
Because, well, I can rearrange it as the properties of commutativity.
If you have an abelian group, then any ordinary subgroup happens to be normal. And the reason for this is abelian in G subgroup, then for all G and G inverse, well, let me say, for all G and G and N in N, G inverse in G group is in G inverse G, which is N, which is an N. And so if you believe this equivalence right here, that's all you gotta know, all right? So if a group's abelian, all of some subgroups are normal. You might ask, hey, is the other way true? Suppose I walk up to you on the street and give you a group and say, hey, look, all the subgroups are normal. Does that mean it has to be abelian? And the answer is no. And you'll see that actually in your homework. So proposition 413. I'm going to repeat what I said a moment ago as part of this proposition. Speak through the notes, and I'll prove the other part. Let G and H be groups. And B from G to H, a homomorphism. One, if E is abelian and N is a subgroup of G, then N normal in G, state we made over there, and 2, the kernel of phi is normal. This is actually a large class of groups that always have to be normal. Is the kernel of homomorphism. This turns out to be incredibly important right here. And this hydra will rear its head many times in the study groups. Let me prove too, because I think it's important for value. Suppose phi from P to H is homomorphism. And let X G and the kernel. It slices show that G inverse X G maternal are all. So this thing, of course, we call this a conjugate of X. What you have to do is show X is in the kernel, any conjugate of X remains in the kernel, and that makes it a normal subgroup. Right, okay with that? You gotta love homomorphisms. Because it's a homomorphism, I can break this up into its piece of parts, right? Right? And what do you know about middle of the Oreo here? That's right. If this is just the identity of H. So we get this according. Squeeze it together again because it's a homomorphism. And this is phi of the identity of G, which is the identity of H. So, conclusion, G inverse XG is an equivalent. So, kernel of P is a normal subgroup. Okay. Everybody else? Now, I'm gonna be fast and loose, a little sloppy here, but I'm gonna come back and just about what I've done. Write some down first. Let A and G be so. If H normal and G, then H is normal, that's happening. That's what it is. Normal. So if I was manipulating this in a very kind of naive way, I might say, hey, look, I can multiply both sides by G. And I get this, right? This is an equivalent way to think about G being normal. These are called cosets, left coset, right coset. Let me formally define these and work some examples, see how they work. So let H be, I don't care if it's normal at this point, I want H to be any subgroup. So definition. Any subgroup, doesn't have to be normal, anyone you want. And GNG. That's any element you want. We're going to define the left coset. So what do I mean by G times H? I think this notation is suggestive. This is a set. The H is a subgroup, so I'm equal to set. And what is this? This is GH as H ranges through the elements of H. So it's basically you take the entire list of everything in H and you put a G on the left side of it and you make a new list of things. This is called a left coset of H in as you might guess, you can find a right coset. This is also a set, but now you run through the elements of H, you put G on the right instead of the left. Okay, so let's, before we get too much in the weeds on this, let's look at let's look at the left cosets. Let's start with this. Here's my playground. Let's look at S3 and then this is a good, very kind of illustrative example of it. I'm going to start off with N. When we did that last time. Let's look at the left cosets. One thing I could do is I could multiply everything on the left by E, couldn't I? Right? And that's my lazy coset. I could do this. I'm gonna please. There we go. Okay, what's this guy here? One goes to 2 back to 1, so I'll erase that 1. 2 goes to 3. 3 goes to 2 to 1. 3 goes to 1 to 2. And finally, this last one, 1 goes to 3, and then it's done. 3 goes to 2 and back to 1, and 2 goes to itself. What's another possible left coset? Notice this coset is the same as this one. Correct? It's in a different order. Anybody want to guess what will the coset 2, 3 times into? It'll be this one, only it'll be in a different order. If you multiply 2, 3 by n, it'll be 2, 3, and then the other 2 elements, whatever you give them. I agree. So actually, there are 2 left cosets. This one and this one. How many elements are in each of the cosets? There's 3 elements in each coset. What's the overlap?
E.
Yeah. It's empty. There's nothing in common. In fact, these 2 left cosets partition G. Right? Everything in G is one and only one of those 2 left cosets. Let's look at the right cosets. Let's do just for fun. This turns out to be 132. These two are inverses of each other, so that's the identity. And this turns out to be 1, 2, 3. Let's do one we haven't done yet. So let's see what we get. Let's see, 1 goes to 2, 2 goes to 1, and 3 should go to itself, and it does. And I'll put pressure parts my anatomy. This is 1, 3. Let's see. 1 goes to 3. 3 goes to 1. I like that. 2 goes to. Notice, I have the same 2 animals, right? This is N again, and this left coset is the same thing as, or I'm sorry, the right coset is the same thing as the left coset back here. All the elements of order 2 are in this one, and the elements of order 3 in the identity are in the other. Everybody agree with that? Every left coset is a right coset as well. Let me contrast that with another. This time, I'm going to look at the subgroup H, which is, we'll let H be. It's easier to get cosets now, but, so let's do the left coset. By the way, this is also equal to the coset 1, 2, H. Do I agree with that? Because if I multiply 1, 2, I get 1, 2, E in the other order. Okay. How about this? Uh, 1, 3, 1, 2. So this is 1, 3. And the other coset, or I'm sorry, the other element, 1 goes to 2, 2 goes to 3, and 3 goes to. You can check if this is also 1, 2, 3. And actually, there's only one more. What am I missing? 2, 3. And this is 2, 3. And let's see, 1 goes to 3, 3 goes to 2, 2 goes back to 1. And this is 1, 3, 2. So these 3 things are the left cosets. Notice, again, this partitions G into 3 easy pieces, all the same size. Do I agree with that? And there's no overlap. 1, 2 is here and only here. 1, 2, 3 is here and only here. Agreed? Let's see what happens when we look at the other side. Let's look at the right cosets. Well, that's the same. Right? But let's look at this. This one goes to three. Three goes to two. Two goes back to one. Notice this right coset is not a left coset. Because over here, 1, 3 is paired with 1, 2, 3, not 1, 3, 2. And this is 2, 3. What the heck is this? I bet this is 1, 2. Let me check that. 1 is 2, 2 is 3, 2. This one right here is also not a right coset because here the 2, 3 is paired with 1, 3, 2, not the opposite. So we kind of switch around some of the elements. The difference is this: for n, every left coset also a right coset. Here, no, it's not true that every left coset is a right coset. That is another important characterization of normal sewage. However, keep in mind this, make this observation, that whether we look at left cosets or right cosets, it partitioned the group. In this case, into 3 equal pieces, right? The 3 pieces here and the 3 pieces here are different, but they're both partitions. Do I agree with that? The union is all of the group and there's no overlap between the separate pieces. So here is a theorem in the spirit of what I just said. There's 4, 6. Let's let H be a subgroup. Collection of left, respectively, right, cosets of H and G form a partition of G. Let me kind of flesh that out a little bit. In other words, G is equal to the union specifically G is the union of all cosets and GIH and if GIA intersect GJH is not empty, then GIH. So all I'm saying right here is the puzzle pieces either have no overlap or they're exactly the same. So if there is some overlap, they have to be exactly the same. Respectively, G is the union of the right cosets and HGI intercept H G J, not empty, implies H G I equals H. So if you're not familiar with this, the way you read this theorem is, forget the respectively. The collection of left cosets forms a partition. Specifically, G is the union of these cosets, and the cosets either have empty intersection or they're exactly the same. And then you can also read this, the collection of right cosets forms a partition. Specifically, G is equal to the union of right cosets, and the right cosets either don't overlap, but they're exactly the same. Okay, any questions on
So because it's a partition, you find an equivalence relation on G as a set,
that?
but it
Yeah,
just
but
doesn't
this
maintain group
This
structure.
is much more than a garden variety equivalence relation, because this has a great deal of symmetry, we're going to see, right? Because given any partition, you can find an equivalence relation and vice versa. But this partition is special. There's a lot of symmetry. See. Before I prove this, let me make a definition. Um, yeah, H and G is inseparable. Then the number of distinct left, respectively right, cosets of H and G is called the index. And it is written so when you see this symbol, it means the index of H and G. That is the number of left cosets of H and G, the number of distinct different ones. This is also the same number as the number of right cosets. We've seen this via example. And actually, in the case where G is a finite group, this is the order of G divided by the order of H, but we'll see that later. We'll actually see that as well. So, okay, so let's go through the proof of this. Proof of 6. Okay, note, if G is an element of G, so pick any element of G, then G is in because the left coset. By the way, I'm only going to prove this for left cosets. Proof for right cosets, just go back and put the on the other side. I make the observation that if I walk up to you on the street with any element of group G, it is in the left coset GH. Why is that? Correct. That's very important. H is itself a subgroup, so the identity is one of the elements of H, right? So G times the identity for G is one of the elements of GH, right? So everybody think that? This makes this statement mean everything in G is in this union, and since GH is a subset of G, then okay so far? We've already got that way. This part good to go. It is true that G is the union of all electric cosets. But now I've got to do the partition. Right? So I've shown the union part of the partition. Now all I have to do is show, by the way, I guess technically, do a partition, you need every one of these pieces to be non-empty. But of course, G times, this is a set, this is a non-empty set, because H is subgroups, so we'll get there. Everybody okay that none of my pieces are empty, right? Now, let's suppose, I, for some X, Y, D, I don't want to use subscripts if I don't have to, I'm a lazy man. Let's suppose that X, H intersect Y, H is not empty. So suppose I have two puzzle pieces, I'll call it X, H, and Y, and suppose I say, hey, there's something in common to that. I want to show that those two are exactly the same, right? Okay, so what does this mean? There exists a Z in XH and YH. Well, so what does this mean? So I can write Z equals XH1 and Z is equal to YH2 or H1, H2 in H. Everybody okay with that? Well, means so X is equal to Y, H2, H1 inverse. Everybody okay with that? So if H is in H, again, XH is Y, H2, H1 inverse of H. Everybody agree with that? So notice what this says. Notice H is an H. Where is this unholy mess of symbols? Where does that live? This also lives in H because all the players here, H2, H1, and its inverse, and H are elements of H. So this is in. So, conclusion, for all H and H, XH is contained in Y capital H. And what does that mean? Well, this means but my choice of X was arbitrary. Reverse the letters. If you just reverse the roles Y and H here, you also get the Y and XH. And left cosets. Indeed, form. Everybody cool?
Would you show the other direction?
What other direction?
Like if they were, oh, I guess there's, hold on.
Okay. So, other questions? Let me make another observation here. Uh, all, well, respectively, right? Cosets of H and G have the same hometown. That is to say, they're all the same size. And this is very much like the kind of thing I might have put in. There's a bijection. That takes X little h, Y little h. So I did not realize I've gone a minute over. I apologize for that. So I'll let you all cogitate that. The math club today should be a lot of fun. It's about generating functions. I encourage you to be there. There should be pizza unless Domino's lets me down. Other than that, y'all have a good weekend, and we will see you on Monday.